Now we will study about electric current. That is, when the charges are in motion, we call it as current electricity. In the previous chapter, we studied about charges which are at rest, and that concept we call it as electrostatics. Now the charges are not static, they are mobile, hence we call it as current electricity. Anything that flows is called as a current. So air current, water current, so they indicate the flow of air or flow of water. So similarly, when there is a flow of charges, we call it as current electricity or electric current. Now you might have seen while lightning, a large amount of current passes either between the clouds or from the cloud to the earth. So through the atmosphere, large amount of charge passes into the earth. So here the current is of very high value and it is not a steady current. So steady current means if the flow is constant, then we call it as steady. So in this chapter, we are going to discuss about the steady currents, not about unsteady currents. So the flow or the rate at which the charge flows through a conductor is steady. Such currents are known as steady currents, about which we are going to study in this chapter. Now, how do you define current? So current is defined as, let us suppose a charge of Q units passes through the cross section of a conductor in a time t, then the rate of flow of charge is defined as electric current. But the flow, if it is not exactly constant, then we define current in the limiting case of small amount of charge crossing a unit cross section in a small time interval. So let us suppose if a charge of delta Q units passes through a cross section of a conductor in a time interval of delta t, then the limiting value of this, that is limit of delta Q by delta t approaching 0. So for a small time interval, how much charge crosses a cross section of a conductor? This flow rate is called as electric current. So this is how we define electric current in general. Now the unit of current is, this is coulombs per second, which is known as ampere. But the unit of current, ampere, is defined according to the magnetic effect of the current, or the magnetic force produced by a current carrying conductor. So in terms of that magnetic force, ampere is defined. This we will study when we study about magnetic effects of current. Or in first year in units and dimensions, you might have learned the definition of ampere in terms of that magnetic force produced by two parallel current carrying conductors. Okay, that is how we define actually ampere. But we can say from this, 1 coulomb of charge passing through a cross section of a conductor in 1 second is defined as 1 ampere. So to understand in a better way how the charge flow takes place in a conductor, so let us consider a cylindrical shape of a solid conductor. We know that in a conductor which is a solid, the electric current or electrical energy is carried by electrons. We call them as free electrons. But in the case of gases and in the case of liquids like electrolytes, we have both negative and positive charge carriers which carry the electrical energy. But we confine here only to the solid conductors. So consider a solid conductor like this. Suppose in the absence of any electric field, it means no force is acting on the free electrons that are present in the conductor. Therefore, what happens? The electrons will be randomly moving in different directions and they will be colliding with each other and their directions will be changing randomly. So they don't have a velocity in any definite direction. Hence, the net rate of flow of charge carriers will be 0. in the absence of any external electric field. So to create an electric field, what we do is we fix the two ends of this conducting cylinder with plates, one side having plus Q charge, the other side having minus Q charge. That is, take dielectric plates of same cross section and give some positive charge to one plate and negative charge, equal negative charge to the other plate, then fix them at the two ends. So imagine like that. Then what happens? A potential difference is created and an electric field acts like this from positive side to negative side. Therefore, the electrons will experience a pull, a force, and hence they travel in the opposite direction. So electrons from the negative end will move to the positive end until the charge on this end is neutralized. This will take very small time. So within a short time, due to the flow of these negative charges, the charge on the positive end gets neutralized. So for a momentary period only, you will observe the electric current. So if you want to have a steady current flowing through the conductor, what you need is a device or a mechanism which is externally arranged, which can supply a constant potential difference or which can apply a constant electric field inside the conductor, and hence for every charge neutralized at one end, an equal charge is produced at the other end, so that the charge concentration remains constant and there will be a steady flow of charge carriers, that is electrons in this space. So that mechanism which maintains a constant potential difference or which produces a constant electric field for the flow of electrons in a conductor is nothing but a cell or a battery. So about which we will study later. Now, the next topic we are supposed to study is Ohm's law. So, this Simon Ohms is a scientist. He discovered a very simple relation between the voltage and current. Even before knowing the actual mechanism of flow of current, the electric current in a conductor, he found a simple relation between the potential difference and the current through a conductor. So, according to this relation, the current flowing through a conductor bears a linear relation with the potential difference. Suppose if V is the potential difference across the ends of a conductor and a current I passes through the conductor, then V is proportional to I. And you can write the equation in the form of this R equal, where R is a constant of proportionality. This constant we call it as electrical resistance. Electrical resistance. And the unit of electrical resistance is Ohm. Unit is Ohm. And you know the symbol? This is the symbol of electrical resistance. So R is equal to V by I. Now this value of R depends not only on the nature of the material of the conductor but also on the dimensions of the conductor. This can be easily understood like this. Consider a rectangular shaped conductor. So suppose So consider a rectangular slab of a conductor, and let us say that it has an area of cross section A and say some length here. Now consider a similar conductor kept side by side. If this conductor carries a current of I and it has a potential difference of say some V, then if you arrange another similar conductor side by side like this along its length of same length and same area of cross section, So if the same current flows through this conductor also, the ends of this conductor also must have the same potential difference. Therefore, for the same current, the potential difference across this entire length, that is, we can write like this. Here, from this formula, R is equal to potential difference by current. So using that, here R of R dash of this two conductors kept side by side along the length is given by 2 times voltage by the same current. But V by I is equal to R, therefore that is equal to 2R. So this means that doubling the length doubles the resistance. That is, electrical resistance directly depends upon the length of the conductor. So this is one relation. And another thing is, you cut the conductor along its length such that the area becomes half. So you cut this rod into 2 pieces of equal area of cross section, and suppose the area has become A by 2 and the length is same. So as a result, what happens? The number of charge carriers becomes half. So if you imagine the charge density is same, if you cut the area of cross section, we can easily assume that the number of charge carriers also will become half. Therefore, current also becomes half. Then in such case, we can write like this, R double dash. So you have to apply the same potential difference. So let us imagine the same potential difference is applied. So then R double dash is equal to here we, and what we have done, the potential difference is same, but current became half. The same block is divided into 2 parts such that area of cross section becomes half. When the area becomes half, the current carrier's number becomes half. So we can put the current as I by 2. In such case, the resistance R double dash will be 2 times V by I. That is 2 times R. That means if the area is half, the resistance is double. That means the resistance is inversely proportional to the area of cross section. Now you can combine this relation and this relation, and you can write like this. R is proportional to length and inversely proportional to area of cross section. So then we can write like this. R is equal to rho into L by A. Here, this quantity rho is called resistivity. This is called as resistivity. And the unit is nothing but from this ohm meter. So that is the unit. So here 1 meter square, the 1 meter gets cancelled, meter square goes to this side. Ohm meter is the unit of resistivity. So resistivity is the property of the conductors which governs the resistance of a conductor. And let us study on what factors the resistivity depends, and also we will study the causes of resistivity in terms of mobility of the charge carriers. Okay, let us discuss about that. And here we can make some more points. Here we can discuss some more points. That is, so R is equal to rho into L by A. That is what we discussed. Therefore, if you write I is V is equal to IR, so we use this formula. V is equal to I into R. So that is I into, in the place of R, I will write rho L by A. Here I by A, I will take it out separately, rho L. And this quantity actually, the current per unit area is called, this current per unit area is called as a current density. Current density, which is represented by a letter J. Okay, so from the formula we derived there R is equal to rho into L by A, and using Ohm's law we substituted for R this formula, and I have written this I by K as a separate quantity called J. In such case I can write it like this: V is equal to J into rho L. Here the relation between the voltage and electric field, you know very well that the that is electric field strength is defined as negative gradient of potential, that is E is equal to delta V by delta L or delta R or delta X, whatever it may be. Therefore V is equal to ED or E into L, where L is the length of the, here you consider a conductor now. So this is a conductor, you apply an electric field. Let us consider the area of cross section of this conductor is A, and the electrons are flowing like this. So an equal amount of positive charge may be considered flowing in the opposite direction. So the potential difference across the ends of the conductor is related to the electric field strength like this, where L is the length of the conductor. Then using this relation, E into L is equal to J rho L. So this L gets cancelled. So this relation is equal to J into rho, and this can be written as J is equal to E by rho. E by rho. So this 1 by rho is written as sigma into E, where sigma is called conductivity. Sigma is called as conductivity. Conductivity. So this is another form of Ohm's law. See, in Ohm's law, what you have done? V is equal to I into R, and here J is equal to sigma into E. Here sigma is nothing but reciprocal of resistivity. So that reciprocal of resistivity, we call it as conductivity. So this we can also call it as another form of Ohm's law, because it is derived from this only. So these two can be treated as equal. So here this can also be represented in different forms. I is equal to V by R, is it not? Current is, if you say 1 by R is a constant, I is proportional to V. Here sigma is proportional, is a constant, then J is proportional to V. So here we can say that current is proportional to potential difference, vice versa. Potential difference is proportional to current. Here current density, J is proportional to E. And you know, J is a vector because electric field strength is a vector. So therefore, current density is also treated as a vector and is in the direction of the electric field. Remember, this is a very important point. The only quantity, physical quantity in current HT is, that is a vector quantity in current HT is the current density. So this is the only quantity which has the vector property in current HT. So if you observe these two, so they appear to be similar. Hence, we say this is another form of Ohm's law. Okay. Now, next in the next topic, we will discuss about the cause of resistivity. What is the reason for the cause of this resistivity? And we will study about drift speed.